So we will be discussing about Fourier analysis. So let us suppose we are having some signal here. Actually, we can say it is a function. It is a function of time. The means time is here independent variable, and this f of t we can say it is the function of this t. So basically, we can say that function is also a signal. But in communication terms, we didn't say it. We didn't say it is a signal because it doesn't represent any information. We have to make it modified with some modulation techniques and so that it represents some information. But let us suppose this is a signal. Signal means with every change in this time domain. Okay, so actually these are the phase values. Means when we move through this x-axis, this consists of the phase. Means when we, let us suppose we are going through this, we are creating one cycle for this signal. So what is one cycle? One cycle means the pattern that it repeats forever. That particular one period, that particular one pattern. So the time it takes to complete that's called the fundamental time period, and the frequency means the inverse of time, means the time it takes to complete that particular pattern. That's called the frequency. Okay, so now what is frequency analysis? Fourier analysis. So Fourier says that, okay, let us suppose we got some signal here. Okay, so this is 1 second, this is 1 second. So now if we give this to Fourier, what Fourier say? Okay, Fourier knows only one thing, that's sinusoidal. So Fourier will pass one signal, that is sinusoidal, it will do 1. So is both the signals same? No, both signals are not same. So why? Because this frequency, this signal's frequency is higher. It completes 2 hertz, means 2 hertz it is the frequency. It completes 2 cycles in one time period. Means 1 second it completes 2 cycles. But this the Fourier done this approximation using this signal. It completes one cycle only in one time period. Means in 1 second it completes only one cycle. So our approximation is not correct. So let us remove this. Now Fourier came again. He told that, okay, I want to approximate it. What he does, previously he approximated it using the 1 hertz. Means he tried to complete it 1 second, one cycle. Now he will complete 2 cycles. Means he is increasing the frequency, and when he is increasing the frequency, he will be able to match all the values here, because now the starting point is same and the ending point is also the same, because this is a periodic signal. Okay, so now it was able to know okay, this signal is actually a sinusoidal signal. It is a sine function, and its frequency is 2 hertz. This is it. So Fourier was able to know the frequency of this signal. It was able to know what type of signal it is. Now suppose there is some another signal that is completing 3 cycles in one means 3 hertz frequency. So now with 1 hertz we will not be able to approximate it. 2 hertz we will not be able to approximate it. We don't know, it is a sine function. With 3 hertz we will be able to exactly match all the pattern. So we'll say this is a 3 hertz signal. Now another signal came. Let's suppose this one. So what's the frequency of this signal? What's the signal? So okay, so Fourier came. Let's suppose this is a 1 second, this is 1 second. So Fourier came, he does this. So he now he calculated the error between this signal and this signal. Are they same? No, they are not same. Now he will calculate the error. So there is an error. Means this part is an error. This part is an error. This part is an error. So somewhere it is matching, but mostly it is having errors. Okay, means we are not able to approximate this function using the 1 hertz. We are not able to approximate it using the 1 hertz. Means 1 cycle in 1 second. Now Fourier done 2 hertz. So will 2 hertz will be able to achieve it? Let's suppose this. No, we will not be able. If we do 3 hertz only, we will not be able to achieve it. Why? Because there is a difference between the amplitude values of this signal and the approximation functions we are using, the sinusoidal functions. So what Fourier is now say? He said that, okay, if there are 2 signals, let's suppose this signal, this is completing 2 hertz. It is 2 hertz. This is completing 2 cycles in 1 second, and another signal is in this same period it is completing only 1. So if we add these 2 signals of difference, this is 2 hertz signal, this is 1 hertz signal, another one will be 3 hertz signal, 5 hertz. If we add these signals, we will be able to get the different the new signal that we will get after adding these signals. The signal we will get, that will not be a sinusoidal function. The problem was in this, the function itself was a sinusoidal, so we are not able to achieve it. Okay, we are not able to approximate it. Why? Because we are trying to specific frequencies, 1 hertz, 2 hertz. So this wasn't the sinusoidal. So how can we say that it is 1 hertz, 2 hertz? It is not sinusoidal function. It is different function. But now Fourier came to know that, okay, the problem is like this signal consists of different frequency components of sinusoidal. Means let us suppose it is consisting of 2 hertz sinusoidal, 1 hertz sinusoidal, 4 hertz sinusoidal, and different components. So what Fourier now say that, okay, let us suppose this we are having this same signal here. So now first thing. So if we are having periodic signal, this pattern is getting repeated. So first we have to identify the pattern. When we identify the pattern, we will know, okay, it is following this pattern, and the complete this pattern it requires some time. That is t. T is means t naught. T naught means fundamental time period, and we know that this relation 2 by f naught. is equal to omega naught. Okay, omega naught is the angular frequency. Angular frequency means this. Let us suppose we are completing this cycle, so we are covering a distance, that is angular distance. Okay, and the frequency will be angular frequency, means how much time we will take to complete one complete cycle. So that is 2 pi f naught. So omega naught is equal to 2 pi f naught. F naught is here, t naught. So we can say that omega naught, this angular frequency, will be equal to 2 pi t naught. So this is the angular frequency of this signal. So we will check with, okay, let us suppose we will check with omega naught. What is omega naught? 2 pi divided by t naught. Now we will check with 2 omega naught, that is 2 multiplied by 2 pi by t naught. So it will be 4 pi by t naught. So it is, we are increasing. Let us suppose this is one sinusoid with 1 hertz. This is with 2 hertz. This is with 4 hertz. So we are what we are actually doing, let us suppose we are having this amplitude values. Okay, these are the amplitude samples. So some particular omega naughts will cover this amplitude. Some will cover this one. Some will cover this one. So we have to actually cover each of the samples, amplitude samples here, and those samples will consist in the frequency domain some frequency coefficients. Okay, let us suppose we have covered some of these two samples we have covered 2 pi by t naught. This is the fundamental frequency. So we will have a peak here. So that peak, how much the peak value will be there, that is determined by how many samples we are having covering with this. So another peak that might be at 4 pi by t naught. So why? Because when we approximate this with 4 pi by t naught, so how many amplitude samples we have, we are able to match with this 4 pi by t naught. So that will be the peak of this in the frequency domain. Okay, so that's for this. We will continue with the next.